in the practical resonance circuit, we have seen if we have one circuit element in one branch and two circuit element in one more branch, how we can simplify and obtain the expression for the resonant frequency, and what will be the expression for the total impedance of the circuit. So we have seen two different cases for the practical parallel resonance circuit. In continuation with that, we will today look into the practical series resonant circuit. So if you look at the circuit here, you have an inductor which is in series with the combination of R and C. So the resistor and the capacitor are connected in parallel, and this combination is in series with the inductor. So let us see what will be the expression for resonant frequency in this case, and what will be the expression for the total impedance of the circuit. Okay, so like the way we have done the derivation for the practical parallel circuit, we need to first consider what is the impedance of each of the circuit element. So we have the first circuit element to be the inductor. So the impedance of the inductor can be written as ZL to be equal to J ZL. Let me name this as equation 1. The impedance of the resistor is ZR is equal to the same thing, that is a resistor itself, and the impedance of the capacitor, let me represent this as ZC to be equal to minus JXC. So I have represented the impedance of each of the circuit element. Now I said this is a practical case of series resonance circuit. So if you observe, the resistor and the capacitor are in parallel. So let us compute what is the equivalent impedance of this parallel combination. So the parallel impedance is computed as, in general case, let me represent this as Zp to be equal to 1 divided by the number of elements that are connected in parallel. So you have 1 by Z1, 1 by Z2, plus so on till 1 by Zn. So if you have n number of branches connected in parallel, this is how you compute the parallel impedance. But in our case, we have only two branches, one which consists of the resistor, the other one which consists of the capacitor. And if you observe the expression for computation of parallel impedance, it is 1 divided by 1 by Z1 plus 1 by Z2 and so on. And since 1 by Z is equal to the admittance Y, I can also write this expression to be equal to 1 divided by Y1 plus Y2 plus Yn. Okay, so using this expression, let me compute the parallel impedance of the combination R and C. So in my case, I have Zp to be equal to 1 divided by 1 by Zr plus 1 by Zc. So that is 1 divided by 1 by R plus 1 by minus JXC. So let us simplify this expression. You can see here there is a term which corresponds to the imaginary part. So what we need to do is we need to rationalize this particular equation. So I can write this Zp to be equal to 1 divided by minus JXC plus R divided by R into minus jxc, right? And this can be written as, let me bring this term to the numerator, r into minus jxc divided by r minus jxc. Okay, let me rationalize this. So on rationalizing, basically the intention is to remove this imaginary part in the denominator. So I can write this as zp to be equal to r into minus jxc divided by r minus jxc multiplied with r plus jxc divided by r plus jxc. So cross multiply this, okay, multiply this, and here you have this as minus jxc into r square minus j square xc square into r divided by r square plus xc square, right? So you can see here j square is present. J square is nothing but equal to minus 1. So I can write this term as plus xc square into r. So this can be written as minus j xc r square plus xc square into r divided by r square plus xc square, that is zp. Is it clear? Okay. Now when we are considering the total impedance of the circuit, so the total impedance of the circuit will be represented as Zt. If you look at the circuit, what did we have? We had an inductor here, and then we had the parallel combination of R and C. So the total impedance of the circuit will be the sum of the impedance of the inductor plus the impedance that was obtained from the parallel combination. So I can write the total impedance to be equal to ZL plus Zp. So ZL, as you can see, we have computed that from equation 1, and that is equal to JXL plus this particular term, that is XC square R minus JXC R square divided by R square plus XC square. Okay. So this is the total impedance. Now because we want to compute the expression for resonant frequency in this case, what we need to do is we need to segregate the real term and the imaginary term. So we can segregate that and write this expression as XC square into R divided by R square plus XC square plus J into XL minus XC square R divided by R square plus XC square. So this is the real part of the equation, and this is the imaginary part of the equation. Now let us equate this imaginary part of the equation and see what happens. So at resonance, as we have seen, the imaginary part of the equation, let me name this as equation number 4. Okay, let me name this as equation number 4. So at resonance, the imaginary part of the equation 4 is equated to 0, and you will have this term XL minus XC square R divided by R square plus XC square to be equal to 0. or I can equate this XL to be equal to XC square R divided by R square plus XC square. So let me write this step directly. XL to be equal to XC into R square divided by R square plus XC square. Because I want to compute the expression for resonant frequency, let me represent this XC and XL in terms of omega. So substituting XL to be equal to omega L and XC to be equal to 1 by omega C, I can write this as omega L equals 1 by omega C R square divided by R square plus 1 by omega C the whole square. Now what I need to do is I need to simplify this particular expression. So simplify this and obtain the expression for omega. So I can write this as omega L to be equal to R square divided by omega C into omega square C square divided by R square omega square C square plus 1. So if you see here, you have omega C, omega square, C and C square gets cancelled. Then you have omega here and a omega that is left out here. So let me rewrite that step once again. So omega L is equal to omega C R square divided by R square omega square C square plus 1. Okay, so this omega and this omega gets cancelled off, and you can take this term here, and this is L into R square omega square C square plus 1 equal to R square into C. Okay, so now let me further simplify this by considering this particular term. Okay, so you have omega square R square L C square plus L is equal to R square C. Because we want a term in terms of omega, bring this L to the right hand side. So doing that, I will get omega square R square L C square to be equal to R square C minus L. Omega square R square L C square is equal to R square C minus L. Fine. Now let me name this as equation star, because I'll be using this particular expression later when I want to compute the total impedance. So that is why let me name this as equation star. Okay. So now because I want expression for omega, I can write this as omega square to be equal to R square C minus L divided by R square L C square R square L C square. It is actually whole divided by. Why I am individually doing divided is because I can cancel some of the terms. Okay, so here you can see I can cancel out R square and C can be cancelled with C square, L can be cancelled with L here, and I have the expression as omega square to be equal to 1 by LC minus 1 by R square C square. Okay, so because I want exactly the expression for omega, At resonance, omega is equal to omega naught, and this can be written as omega naught to be equal to square root of 1 by LC minus 1 by R square C square. So this is the final expression for the resonant frequency. Okay. Now if you look at this particular expression, you will see that the resonant frequency has the term 1 by R square C square. So let us see what condition will make it omega naught to be equal to square root of 1 by LC. Now if I am considering this particular term 1 by R square C square to be equal to 0, then omega naught will be equal to 1 by root LC. Whereas if I am considering this particular term, that is 1 by R square C square to be equal to 1 by LC, then the entire omega naught expression will go off, and what I obtain finally will be the expression for ZT. Okay, this entire imaginary part of the equation is eliminated and you have only the expression for ZT. So ZT in that case will be equal to only the real part, which is corresponding to XC square R divided by R square plus XC square. So I can write this as XC square R divided by R square plus XC square. Now let me compute what will be the value of this particular total impedance of the circuit. So I can write this as ZT to be equal to XC square R divided by R square plus XC square. Let me again substitute for omega in this case. So we have XC to be equal to 1 by omega C and XL to be equal to omega L, right? In this case we are not using the XL equation, so let me just eliminate that. Substitute for XC. So ZT is equal to 1 by omega C the whole square into R divided by R square plus 1 by omega C the whole square. Okay, so this is written as R divided by omega square C square multiplied with omega square C square by R square omega square C square plus 1. So these terms completely get cancelled off and ZT equation will be equal to R divided by R square omega square C square plus 1. Okay, now I told you we need to remember this particular equation. So you have omega square R square LC square to be equal to R square C minus L, right? So what I see here in this particular expression is R square omega square C square. So to compute you can utilize this equation. So from equation star you have omega square r square LC square to be equal to r square C minus L, or I can write this as omega square r square C square to be equal to r square C minus L divided by L. So you can see we have this particular term here. So substitute this equal to r divided by r square C minus L divided by L plus 1. So I can write this expression for total impedance at T to be equal to R into L divided by R square C minus L plus L, because I have taken common here and brought this to the numerator. So what remains in this case is this and this gets cancelled off. So here ZT will be equal to RL divided by R square C, or I can write this as ZT to be equal to L divided by RC. So this is the expression for the total impedance at resonance. Clear? Is everyone clear? So this is the way we have derived for the other circuits also, the parallel circuits as well. Okay, and in all of these cases we have obtained the expression for the total impedance of the circuit and the expression for the resonant frequency. The main important thing that you need to note here is at resonance we are considering the imaginary part of the equation to be equal to 0, and that is when we get expression for omega naught. Okay, so here you can see, if you consider the condition this value to be equal to 0, then you will get omega naught to be equal to 1 by root LC. If not, if you are considering this to be equal to this entire term will disappear. Then what we are doing is, you know that at resonance the imaginary part of the equation is 0. So what exists is only the real part of the expression 4. We are considering that real part of the expression, substituting for XC in terms of omega, considering the expression for omega and the remaining part of the expression, that is omega square r square C square. It will vary from derivation to derivation. Okay, just substitute that and obtain the final expression. The question which is being asked to solve a numerical. If you observe the circuit here, they have specified that we need to show that the circuit is resonant at supply frequency. From mere observation, if you see, you have an inductor, you have a resistor and a capacitor. The resistor and the capacitor are connected in parallel. So this parallel combination is in series with the inductor. So this circuit is much of a practical case of series resonance, right? So from this circuit, what I see is, you have the voltage that is being specified to be equal to 10 cos 1.4 t, and this is the supply voltage, and I can write this in terms of omega as 10 cos omega t. So the supply frequency that is being given here is equal to 1.4, that is equal to omega in radians per second. Clear? Now I need to compute or show that the circuit is resonant at supply frequency. because we have just derived the expression, let me consider the expression directly. Okay, if not, in the numerical what you have to do is you are supposed to consider the imaginary part of the expression, that is this imaginary part of the expression, derive up till here, then compute what is the resonant frequency. Once you obtain the expression, omega naught is equal to square root of 1 by LC minus 1 by R square C square. But because we have just completed the derivation, let me write the expression directly. I have the expression of resonant frequency of this particular circuit as omega naught to be equal to square root of 1 by LC minus 1 by R square C square. Okay. Now in the question they have given you the values of L to be equal to 0.5 Henry, C to be equal to 1 farad and R to be equal to 5 ohms. So substitute the value and obtain the result. So omega naught is equal to 1 by 0.5 into 1 minus 1 divided by 1 by 5 square into 1 square. See what you get. .4. Okay, so you get the result as 1.4, and since this is in terms of angular frequency, this is 1.4 radians per second. Okay, and clearly you can see, hence the resonant frequency that is obtained mathematically is equal to the supply frequency. Clear? Now the same numerical, you might say that we have derived the expressions for omega naught, right, previously, not in the practical cases. When we saw the series resonance and parallel resonance, the expression was omega naught to be equal to square root of 1 by LC. That is only this particular term. If you use that particular term, you might get the result somewhere as 1.4114 something. Okay, this will be incorrect because for this particular circuit we have the term in addition, that is 1 by R square C square, which will precisely give you the value of 1.4 radians per second. Is that understood? Yes or no? Okay. So now that completes the module, but we will look into the solution to some of the numericals, because we have solved many numericals, but let us see if the numericals are in this form, wherein we have to rearrange the circuit. First we need to identify whether the circuit is a series resonance circuit or whether it is a parallel resonance circuit or no. Okay, so here you can see the first circuit that we have specified. These circuits whichever I have specified here are mainly using the concept of source transformation. Okay, so you can see here this is basically a series resonance circuit. Okay, wherein you have a resistor, that is 5 ohms, capacitor and an inductor connected in series, and what they have done is in between they have used a resistor in parallel with the current source. So you need to transform this particular current source into a voltage source and then you can solve. So the equivalent circuit in this case will be a voltage source, that is of 15 volts. You have a resistance 5 ohms, voltage V1, and this has to be transformed into a voltage source. The resistance will be obviously connected in series. This is 10 ohms resistance, and since this is a dependent current source, so you will have a dependent voltage source in series with 4 Henry, and you have a capacitor that is 1 by 4 microfarad. Okay. Now when you are writing the expression for the voltage source, this is equal to V is equal to I into R. Here the current I was 0.5 V1 into the value of resistance, that is 10. So this is equal to 5 V1. Now clearly you can see this is a series resonance circuit. So whatever parameters are asked in the question, just compute those parameters. Okay. Here basically I am not giving you the question to solve. I'm just telling you that these are the ways in which a numerical can also come. Okay. Mainly these numericals that I have put up in this slide are focusing on the conversion of the circuit after identifying whether it is series resonance or parallel resonance. Okay. Then you have a circuit here. Again, if you observe, you have a resistor and you have an inductor, and there is a current source in parallel with the capacitor. So what you can do here is convert this. So this can be converted into again a dependent voltage source. You have a capacitor, a resistor and an inductor. So this would be the equivalent circuit, which is basically a series resonant circuit. Okay. And in this case you will be computing the value of this particular voltage V to be equal to I into XC. Okay, because you are considering the capacitor, so you have to consider the capacitive reactance, and this will be equal to V is equal to I in this case was 0.3 VR XC, like I can write this as omega C. So this is the value, and 0.3 VR divided by omega C. Okay. So remember one thing, whether you are using this circuit or whether you are solving the other circuit, whenever you have capacitance and whenever you have inductance, you have to represent them in terms of their impedances. Okay, so solution has to be in terms of the impedances here as well. Okay, now moving on to the third type of the circuit. If you look at this particular circuit, you have an inductor, a capacitor, and I can write the equivalent resistance of this particular combination which is in series as 20 plus 80, which is equal to 100. Okay, so the series resistance can be written as 20k plus 80k, that is equal to 100k. If I have to simplify this after transformation, that is combining the series resistance, I have this as 400 microhenry, a capacitor connected with an equivalent resistance, that is RS. Here you have 100 picofarad and you have 1 millivolt. Now if you look at this particular circuit and the concept that we have studied today, this might look more like a practical series resonance circuit. If you see, you have an inductor, you have a capacitor, you have a resistor. Okay, right? So if you look at the concept that we have seen today, that is this one, you had an inductor, a resistor and a capacitor in parallel. So the circuit that we are looking into might look something like this. Okay, now not always you will be able to know or derive the expression for the total impedance and obtain the expression for the resonant frequency, right? So in such a case, what you can do is, whenever a circuit is given like this, you can see here you have a voltage source in series with the inductor, right? So what you can do is transform this into a current source. So when you transform this into a current source, what happens is that the entire circuit gets converted into a parallel circuit. So I can write this or redraw this particular circuit as a current source in parallel with the inductor, in parallel with the capacitor, in parallel with the resistor. Okay, so this will be the capacitor 100 picofarad, the inductor is 400 microhenry, and the current is computed as I to be equal to V divided by, because the inductor was the one which was in series, it is V divided by XL. Okay, so in this case value of this was 1 milli, XL is omega L. Okay, so the value of the current will be 1 millivolt divided by omega L. So remember, any circuit, okay, because we have seen practical cases, right? We have seen practical cases, but when you solve numericals, those practical cases, each time you cannot derive those derivations, right? Like the way it was asked here, in this case, they have said that show that the circuit is resonant at supply frequency. So basically what you need to do is you need to derive the expression for resonant frequency, and then you have to compute the value equal to this. Okay, now each time it's not possible, so that is why I'm saying whenever there is a possibility of source transformation, solve or convert it into a current source or a voltage source and try to represent it as an ideal series resonant circuit and an ideal parallel resonant circuit, so that it's easier for you to solve the numerical.